what is the brain? The neuroscientists among you may be very puzzled, because usually you're not interested in what is the brain. What you're really interested in is how does the brain function. So you will ask how questions. They address the mechanisms and processes by means of which, for instance, the brain generates consciousness. What questions are for the philosophers? They ask, what is the nature of something? What is it? What is the brain? And for instance, a philosopher will ask, come on, the brain is just a gray, pulpy, gruesome mass, as the German philosopher Arthur Schopenhauer said it in the 19th century. I add, maybe just a gruesome mass. And how is it possible that such a gray, gruesome mass constitutes something like consciousness? To address this question, I will now first think about the question, what is the brain? Let me go into the history of neuroscience. The brain has often been considered as a purely behavioral cognitive reflex apparatus. For instance, Charles Sherrington, famous neurologist and neuroscientist at the beginning of the 20th century in Britain. He mainly focused on sensory motor function and said there's a stimulus, they induce sensory motor functions. Let me exemplify this. You have this beautiful painting. You know, it's a painting from a famous Norwegian painter, Edvard Munch, The Scream. And this painting may actually serve as a stimulus. As you may know, this painting has disappeared from the museum in Oslo for some years. I enjoyed it every evening in my basement before I decided to return it to the museum in Oslo. So, and when I was sitting in my basement watching this painting, my brain got obviously activated. So this is what you call my brain produced something what the neuroscientists call stimulus-induced activity or task-evoked activity. What is important here, that this task-evoked or stimulus-induced activity is supposed to be completely and exclusively determined by the task or the stimulus itself. So that means that the brain itself has no say in what actually happens in the brain. So it's like your car in the garage. The car stands still. Once you hit the gas pedal, the car moves. Without you hitting the gas pedal, nothing happens in the car. Your car is a pure reflex apparatus, similar like the brain. Much of current cognitive neuroscience or social and affective neuroscience basically considers the brain more or less in this way. It associates the neural activity in particular networks or regions with the respective task or stimuli the experimenter applies. But nothing without alternatives. Very early on, a student of Charles Sherrington, Graham Brown, already observed at the level of the spinal cord some spontaneous activity changes unrelated to movement. That is strange. No movement, but activity changes in the spinal cord? That is strange, at least from a reflexive point of view. Other authors like Carl Leschly, neuroscientist and psychologist in the first half of the 20th century, picked that up and developed theories of brain function. But more recently, the view of an active or intrinsic activity in the brain itself, independent of any specific stimuli, has gained more traction. People like Rudolf Linas, Robert Schulman, or Jörg Panksepp, or also Markus Reckl, observed intrinsic activity changes in the brain. Let me sketch this. Now, we start with the brain itself. We start with its intrinsic activity, as symbolized here by the dark blue lines. And with that intrinsic activity, you approach the stimulus. This is very normal. So if you're in a good mood, you have no problems in encountering let's say, a harsh cold winter, as for instance in Ottawa in Canada at the end of March, when you happen to live there. If in contrast you're in a very bad mood, you might really be affected by the same cold. The winter or the stimulus is the same. Each time minus 30 degrees. Blue sky, but freezingly cold and harsh wind from the north. If you're in a good mood, you enjoy the blue sky. If you're in a bad mood, exactly the same weather just gets on your nerves and you just want to stay in bed. So it is really your own mood / your brain's intrinsic activity which makes the difference. And you see in the both cases I sketched, you probably have different levels of task-evoked activity. That cannot come from the stimulus itself, because that is the same in each case. So that means your stimulus or task-evoked activity results from a particular interaction between the resting state and the stimulus. So that means your brain has a strong say in what happens in the brain. Imagine you enter in your garage and suddenly you see your car moving. You haven't pushed the gas pedal at all, but you see your bike or your car moving. You say, this is strange. And then, what do? You want to get into the car, or you want to get onto your bike. So what do? You try to figure out how the brain moves, and you have to adapt. How the car moves, or the bike moves. And then you have to jump on the bike, or you have to you open the door and try to jump into the car. So meaning, your action is very much determined by the action of the car or the bike, of the intrinsic activity. Same. What the stimulus can induce in the brain depends very much on how the brain moves. Yeah? Same thing. So your intrinsic activity. So the question is now, why and how is this intrinsic activity relevant for consciousness? Let me draw the analogy to a famous philosopher, Immanuel Kant, in the 18th century, German philosopher. He suggested that the mind, what he called mind at the time, provide a specific input to our cognition and knowledge of the world. He said that the mind structures and organizes the incoming stimuli from the environment, and that without this structuring, organizing feature of the mind's input, as he said, consciousness cannot be assigned to the stimuli. So meaning, without the mind and its intrinsic activity, you would not have any consciousness at all. So now, apply the same to the brain. Why and how is the brain's intrinsic activity relevant? Because maybe without the brain's intrinsic activity, you would not have consciousness at all. The stimuli might still induce some activity in your brain, but that activity would not be associated with consciousness anymore. So basically the difference between the two scenarios in your garage. The moving bike or the moving car versus a still standing car and bike. The one has intrinsic activity, the other one not. And that's a difference following Kant and its application to the brain, which makes a difference between consciousness and non-consciousness. I will try to lend some empirical support to that idea in the following. So, let me compare the current situation about our knowledge to the pancreas. You know, the pancreas is an organ in our stomach, here in our belly, and you know that the pancreas produces insulin. And the insulin modulates the level of glucose, and that in turn, the glucose modulates various functions throughout the body. If, for instance, you have diabetes, you have too high levels of glucose, and then you can have various symptoms throughout the whole body. You have dark feet, called gangrene, you can have eye problems, and various other symptoms. This is called diabetes. And the diabetes can be traced back to a deficit in insulin. The pancreas does not excrete sufficient insulin for various reasons. That cannot down-modulate the level of glucose, and that in turn causes the various symptoms. Now, how does that relate to the brain? This is sketched on the right. You have the brain and you have a resting state or an intrinsic activity. That somehow modulates stimulus-induced activity, the exact mechanism of which we currently do not know. This is really new territory. There's a lot of investigation in current neuroscience, and I will show you some of our own studies on that, but the exact mechanisms are really unknown. And then that task-induced activity is somehow assigned with consciousness. Why and how? Big question mark. But in consciousness, as particularly if you're a philosopher of mind, you may know, is characterized by different features, as for instance, intentionality. It's always directed towards a particular content, whether mental or physical content, or the famous qualia. What is it like to be a bed? A particular quality in your subjective experience, which only you can experience. For instance, the feeling of laziness or the feeling of boredom. Unfortunately, your neighbor or I cannot experience that when you experience boredom while listening to this talk. So you see what is so well known in the case of the pancreas and diabetes. We don't know really yet in the case of the brain. We somehow know something about the main players. We suppose that they are maybe main players, but how they are connected is very much unknown. I will show you in the following some empirical evidence. So, let me go back to the empirical point of view. Often in the empirical research on consciousness, people presuppose a bidimensional view of consciousness. You have the contents of consciousness. For instance, while you watch this talk, I hope that you are fully conscious, the talk is the content of your consciousness. This is the content of consciousness. For instance, when you are in sleep, you have two different kinds of sleep. You have a REM sleep and a non-REM sleep. In the REM sleep, you have strong dreams. Dreams are usually characterized by content. Whereas in non-REM sleep, you do not dream. You don't have much content. So you see that's on the level of the degree of content. The REM sleep is here. The non-REM sleep is there. That's the simple part. But suddenly, while watching this talk, you may become tired. Oh God, I heard this guy already long enough. Enough. The textbook is boring. The talks are even more boring. Okay, go home. And you drowse and you fell asleep. Okay, not too long, because at least you should be awake at the end of the talk. So, that means your level of consciousness decreases. So, your level of consciousness decreases, and this is what is called a level of consciousness. An example for a decreased level of consciousness is, for instance, in vegetative state patients. I will come back to that, who by definition lost their consciousness. So, the question is now, how can we relate these two different dimensions to neuronal mechanisms? To see what are the neuronal mechanisms underlying consciousness. And I will start with the contents of consciousness, then come to the level of consciousness, and then I will show you that we probably need to introduce a third dimension, the form or structure of consciousness. Let me start with the more easy part, the contents of consciousness. This is a study which one of my postdoctoral students, Christine Wiebking, conducted, and she was particularly interested in contents which originate in the outside world, meaning external awareness. So your awareness is shifted on external contents, for instance, on the talk. Whereas you have also internal contents, for instance, your own body or your heart rate. You hear your heart beating. It's an internally generated content. Both can come to your awareness. For instance, when you pay attention to the talk, I hope so, that the talk is an external content. in your awareness. Whereas if you're very afraid and you have acute anxiety and you think about all your exams you have to go through when listening to this talk, suddenly your heart rate, your heart is pounding and all your attention and awareness is directed towards your heart rate, your pounding heart. And it distracted from the external content, the talk itself. So this can be called internal versus external awareness. And what she did, she tested these two forms of awareness. Either she let subjects evaluate the own heartbeat. That's an internal content in your awareness. So you had to count your own heartbeat, perceive your own heartbeat. Or you had to perceive tones which were simultaneously played. Direct your awareness either towards the own heart or the tones. And then you could measure the neuronal activity during that. That's what she did in functional magnetic resonance imaging, short fMRI. And then she wanted to see how much these regions, these two forms of awareness, internal and external awareness, relate to the resting state activity, to the ongoing resting state activity or intrinsic activity of the brain. For that, she subtracted those two conditions from a resting state condition, like here, a fixation cross. And what she could see is very typical. She could see a lot of activity changes, meaning negative activity changes, so-called deactivation, in the midline regions of the brain. So basically, these signal changes signify that you have decreased activity levels during internal or external awareness when compared to the ongoing resting state activity. Meaning, your resting state activity in these regions is so high that when you shift your awareness towards either internal or external contents, you can only lower your activity. And that change in activity signals your internal or external awareness. And most interestingly, what she showed here is that both internal and external awareness, heartbeat or the tone from the environment, the heartbeat from their own body, induced more or less similar changes in these midline regions. So now you say, this is strange. Because how then can we distinguish whether our awareness is on the external tone or on the own heartbeat? Or whether I'm aware of your talk or of my own heart? So how can you make that distinction? For that, Christine Wiebking did yet another investigation with the same subject. She measured a particular receptor type, the biochemical substance and its entrance doors in the brain, so-called receptors, the GABA-A receptors. And she measured them in exactly those regions where they induce changes from the resting state activity. And this is what you can see here, particularly here in the middle. She demonstrated that the higher your activity changes during the external awareness, the more GABA-A receptors you had. So meaning the degree of GABA-A receptors tells you the degree of activity change during external awareness. Whereas that is the blue curve. The red curve is the same curve for internal awareness. And you do not see any relationship. So meaning the GABA-A receptors seem to particularly mediate the activity changes during external contents. So when you suddenly decide, oh, maybe it's not too bad at least to pay attention to this and the next slide, your GABA-A receptors are important. If in contrast, you just stay focus on your own heartbeat while not listening to this talk, your GABA-A receptors may not be recruited. So, and the same could be observed for the two midline regions. So what do these data tell us? Interestingly, that GABA-A receptors, and GABA is a biochemical substance, seems to mediate specifically external rather than interoceptive awareness, external contents rather than internal content, in specifically these midline regions. So the question is, whether GABA is really important for the shift of awareness to external content. If you cannot recruit your GABA, or if you do not have enough GABA, you may be stuck in your awareness to the internal content, to your own heartbeat. And that is strongly supported by, for instance, patients with anxiety who suffer from GABA-A receptor deficits and have an increased awareness of their own heartbeat. So there you can see that the basic research about the contents of consciousness ties up with clinical observations. So let's go back to our bidimensional view. What I showed you is one study on the contents of consciousness. Obviously, there are many, many different studies on the contents of consciousness, unconscious versus conscious contents, for instance, or as we did it, different kinds of contents in consciousness, like internal or external contents. So you can see you have a variety of different possibilities here. How about the level of consciousness? The level describes basically your arousal. So let's say you drown during this talk, you fell asleep and you become tired. Your level of consciousness decreases. So happy sleep. So how can you test this? One possibility is you investigate patients with vegetative state. What is vegetative state? These patients usually suffer from brain lesions, often, for instance, in the case of young people with motorbike accidents, unfortunately. And they are no longer conscious. They don't behave, they don't speak, they don't move, but they're still alive. A prominent example of that is, for instance, Michael Schumacher, the Formula One driver, who between Christmas and New Year had a ski accident, and since then he's in a vegetative state or coma. So now, you can distinguish between, this is a loss of consciousness, and clinically one can distinguish between different levels of the loss of consciousness. When you don't have any consciousness at all anymore, you have no signs at all, not even eye movements, you're in a coma. If you still have some eye movements but no other signs of consciousness, you have vegetative state. If you have a little bit more reaction, you have a minimally conscious state. So the question is now, how can we investigate these patients? There have been several investigations of these patients in the last 10 years. We did a particular study, this is done by Pengming Qin, a postdoctoral student from China in my group. He was particularly interested in the effects of the own name in these patients. So the own name is, of course, obviously, I assume, at least for everybody of you also, is a personally relevant or self-related stimuli. Nothing can be closer to your own self than your own name. So he was now saying, if these patients show some activity to the self, how important is that for their level of consciousness? So what he did, he presented these subjects with their own name and compared it with another person's name. So, and what he observed is very fascinating, because he should show that basically all the patients still showed some activity changes in response to the own name, but not in response to another person's name. So when I call, like say, the German Chancellor Angela Merkel, when I call her Angela, she will show some activity even if she is vegetative. But if I call her Marina, she will not respond in her brain. So this is what you could see here. You could see that particularly in the regions in the middle of your brain, in the particular region which is here, the anterior cingulate cortex, ACC, and the different portions of it, are recruited when listening to the own names. And you could also see, and here is an overview of all the different regions in the different subjects activated during the own name, and here you have the single subjects. And what you also could show that patients with a higher level of consciousness, like a minimally conscious state, showed a stronger activity in response to the own name. So most interestingly, he then correlated the neural activity during the own name, as here, with the level of consciousness measured in a consciousness scale, the conscious recovery scale revised, here on the y-axis. And you could see the following relationship. The higher the neural activity during self, the higher the level of consciousness in this particular region. So this is scientifically interesting because it tells you maybe the self is very important for your level of consciousness. And second, it is clinically very important because it might provide you a predictive marker of consciousness. And that's what you need. And how they respond to possible therapy. So, now you might criticize and say maybe all the activity changes you observed are an artifact here. Because the subjects merely had to listen passively to the stimulus. You cannot exclude that the activity is not related to the self-stimulus, but to some other ongoing activity when the stimulus is presented. So this is why another postdoctoral student of mine, Zirui Huang, conducted another study in these vegetative patients. And he now investigated the active component. So he presented the subject with questions, self-referential questions, like, have you been to Beijing? So this study was conducted again in the study. So have you been to Beijing? So you have to think about it, yes or no. And these questions were obviously obtained by the relatives. So have you been to Beijing? And then if you say, you can say yes. And when reading the questions, and you answer yes or no, and they cannot answer because they cannot behave. And compared that with non-self-referential question is 1 minute, 60 seconds. So if you see a difference between these two, self and non-self-referential questions in the neuronal activity, it can only be due to the self and not due to some other component. And in addition, he also investigated the resting state activity in these subjects. So let me show you. So what you could see, I unfortunately forgot the slide here, that you could see a difference between vegetative patients and healthy subjects in, again, the cortical midline structures. So the vegetative patients still had some activity during self and non-self. They could somehow neuronally differentiate self and non-self, but that difference was lower than in healthy subjects. And then he conducted a correlation with the level of consciousness here in the perigenial anterior cingulate cortex. This is here, anterior midline region, and the posterior cingulate cortex is here in the posterior midline. And what he showed that the higher the degree of neuronal differentiation between self and non-self, the higher the degree of consciousness. So again, you could confirm these predictive markers, and this is, of course, clinically relevant. So now, how does that relate to previous investigations that have also shown that these vegetative patients show activity during, for instance, stimuli which induce them to play tennis in their imaginations or to navigate through their house. These studies could show stimulus-induced activity like here during self and non-self, but that was not directly correlated with the degree of consciousness. So that suggests that the self may have a specific relation to consciousness. Why and how? Zirui Hong also investigated the resting state activity in these patients. In particular, what he investigated is the degree of continuous change. As I said, remember the initial slides. Your car in the garage constantly moves back and forth. Your bike is suddenly rolling back and forth. It never stands still. Same with the brain. The brain stands never still. There's continuous activity change. The level of activity in the resting state continuously changes. the functional connectivity and the variability, there's continuous change. So now, how about this change in the vegetative state patients? Previous studies show that the functional connectivity, the relationship between different regions, is decreased in these patients. What they did not show is whether there is less change, degree of change, less variability, as you call it, in these patients in their resting state. This is exactly what he could demonstrate for the first time. So he showed that particularly in the midline regions, you can see here again the posterior cingulate and the perigenital antercingulate cortex, anterior, posterior, here and here, showed decreased activity change, meaning your bike or the car is no longer moving around as much as it used to be. There is less change, less variability. It's more tied to a particular position and doesn't move around as much anymore. Meaning the brain's resting state activity doesn't change as much anymore. There is decreased variability, or as we call it, amplitude of low frequency fluctuations is decreased. So now, and then you have these frequency changes, in particular, these activity changes, in particular frequency ranges. So the frequency range we're talking about here is about 0.001 to 0.1. And you can subdivide this in different frequency bands. These are called slow 4 and slow 5. And you can see that the patients show, particularly in the very low frequency band, slow 5, significant less variability. And that holds for this both regions. Now, how does this decrease in change or variability of the resting state is related to the stimulus or task-evoked activity during the self-relevant stimuli? And this is the interesting thing, what he could observe, that the more variability you have here on the y-axis, as signified by the alpha, the higher your degree of differentiation and stimulus-induced activity during self versus non-self, as here on the x-axis. Meaning higher variability in the resting state, more change leads to higher stimulus-induced activity. Meaning when your bike moves around in a fair way, you have a higher likelihood of picking up the bike and riding it. Meaning if your brain exhibits a lot of change, the stimulus has a higher likelihood of being processed in the brain and, analogous to your bike, riding the brain's neuronal activity. It's stimulus-induced activity. So there you have a direct relationship between self and consciousness. And I pass on these slides. So now you might question, how is this now related to consciousness? You may remember that exactly these regions where we showed the decreased variability, the self-non-self stimulus-induced activity predicted the degree of consciousness. Hence, we have a linkage from the resting state activity to stimulus-induced activity. Decreased variability, decreased stimulus-induced activity. And decreased stimulus-induced activity predicts the degree of consciousness, your level of consciousness. So you say that the resting state is not directly related to consciousness, but it seems to be indispensable. Because if you have normal activity change and variability, your stimulus-induced activity can be normal, and then you can have a normal level of consciousness. So let me signify and explain this by the following picture. You have your intrinsic activity. That's what you start with. And that intrinsic activity, called resting state, is characterized biochemically or physiologically by an imbalance between neuronal excitation and inhibition. And for that, two specific biochemicals like GABA and glutamate are very important. You may remember the GABA we had in the contents of consciousness. So, and on the other hand, there is an overlap, which I didn't show here. There's an overlap between self and resting state. And with that resting state, you approach the external stimuli come. So here you see the external stimuli, and they seem to somehow modulate or impinge upon the brain's resting state activity, and that can be called rest-stimulus interaction. And that in turn, that interaction needs to occur in a specific way. The specific ways and the mechanisms which we do not know currently. We are working a lot in our current experiments on exactly this. And that in turn might induce a consciousness of the external stimulus, meaning consciousness will be assigned to your stimulus-induced activity. And at the same time, while you experience these stimuli, like for instance, while you watch and experience this talk, hopefully in a conscious way, you also sense yourself, because it is you who experiences. It is you as subject. So your consciousness of this talk goes along with the sense of self or consciousness of yourself. The two always go together. The content of consciousness and the subject of consciousness. The experience of the content and the somehow experience of the subject. The subject may either recede in the background of your experience, but it's always there. Oh, you watch at the talk, and suddenly you become, it's me. And then your attention is focused towards your own self, away from the talk. Okay, focus your attention back on the talk, please. So, what now the question is, why and how can the resting state be relevant for consciousness? Our own data shows this, other data shows this, that the resting state is important for consciousness. Why and how? We currently do not know. Let me provide you some ideas and suggestions. Remember the bidimensional categorization of consciousness, the level and content of consciousness. The content is clearly associated with task-evoked activity, because it's by means of the stimuli and their respective activity that the content can come into consciousness. In the case of the level, it's somehow unclear. That might be a contribution from the brain itself. So, let me make another comparison. You may remember that I drew the comparison between the pancreas and the brain. Now, I do another comparison between brittle objects and the brain. Let's start here on the left, the brittle objects. Brittle objects have certain features, intrinsic features. For instance, an irregular crystal alignment, and which somehow predisposes it to brittleness and to become shattered. And then you have a certain brittleness, but your crystal is still not shattered. Only when you apply an extrinsic force, an external force, you shatter the crystal. But if the crystal has not an irregular alignment, it is not brittle, you can apply as much force as you want, you will not shatter the crystal. So you have a certain irregular crystal alignment and brittleness on the side of the crystal as an intrinsic feature of the crystal. And you have to have an extrinsic force to finally shatter your crystal. One without the other without the one, will not shatter the crystal. So basically, if you want to say, it's like dancing. Imagine you dance a tango. In the tango, it's always two people move together. If only the female dances a tango, it's not a real tango. If only the male dances a tango, it's not a real tango. So you always need two. As we say, it's a pas de deux. So you always need two. Same here in the case of the crystal. And now same in the case of the brain. We know that here, instead of shattering, we want consciousness, which can sometimes be also a quite shattering experience. And we also know that certain extrinsic stimuli, remember like the painting, or other stimuli, or like the view of a crystal, for instance, may induce consciousness. But in the same way, it becomes more and more clear that the extrinsic stimulus alone is apparently not sufficient to induce consciousness by itself. So for that, we apparently need yet another factor. So now, this leads us back to the brain and maybe its intrinsic features. And one of those may be, for instance, the resting state activity or the intrinsic activity. And apparently, as in the case of the crystal, the intrinsic activity of the brain needs to somehow interact with the extrinsic stimuli to produce consciousness. By itself, neither the extrinsic stimulus nor the intrinsic activity can produce consciousness. In the same way that the crystal alone in its brittleness or the extrinsic force alone can neither produce the shattering of the crystal. So again, like in the case of the tango, it seems to be a pas de deux between intrinsic resting state activity and extrinsic stimulus in the case of consciousness. So that basically means that raises the question, what does the brain's intrinsic activity provide to make possible consciousness? We had so far the level and the content of consciousness, but there must be something different. So what does the intrinsic activity provide? So, and I would argue, you may remember my reference to Immanuel Kant, where the mind structures and organizes the stimuli in such a way to make possible their association with consciousness. So same now in the case of consciousness. The brain might provide a particular form or organization on the basis of its intrinsic activity, a particular spatial and temporal form exhibited and constructed by the brain's intrinsic activity, into which the stimulus needs to be integrated, and that integration makes possible its association with consciousness. So we have to have another dimension, besides level and content of consciousness, a form of consciousness. This is what I called a tri-dimensional view in a recent paper last year. So, and you can already see that that is very close to the concept of mind as Kant suggested. Now I transfer some of his ideas to the brain and see whether that is empirically plausible. Okay, let me give you a little bit more meat to the bones. For instance, we know that our brain's intrinsic activity has is continuously active and changes. It exhibits particular fluctuations of neuronal activity in different frequency bands, indicated by the red bars. And these different frequency fluctuations are somehow coupled with each other. So they provide certain phase durations or cycle durations. And now when you have external stimuli, these may be somehow integrated or processed or linked by these different frequency fluctuations. So if they fall into the same frequency fluctuations and the cycle duration, certain stimuli might be linked, and certain others may be linked again, but distinguished from the first one. So you can see by that different kinds of stimuli can be tied and bound together by the intrinsic activity and its particular temporal structure, if you want to say so, of its frequency fluctuations. So, and that's exactly what you see in consciousness. You have a binding together of different stimuli. And then you experience a certain time, what phenomenologists call inner time consciousness, and you can develop specific hypotheses, as for instance signified here. The phase durations of low frequency fluctuations is directly related to the experience of the duration of a particular tone. So if you have a longer frequency fluctuation with a longer cycle duration and the tone falls into that, you might experience the tone in a longer way than it actually physically is. So I don't want to go into detail, but you can develop specific hypothesis about the linkage between neuronal mechanism, here on the y-axis, and phenomenal features as you experience consciousness. The same you can do on the spatial side, that by means of the functional connectivity between different regions and network, the different stimuli are grouped together or not grouped together. So stimuli, which sometimes maybe not even belong together originally, may be grouped together by the functional connectivity or the low frequency fluctuation. And this is exactly what you experience in consciousness. So coming back, the brain's intrinsic activity might provide its own spatial and temporal structure to organize and structure the incoming stimuli. And the better the latter, the incoming stimuli are structured and organized and integrated within the spatial temporal structure of the brain's intrinsic activity, the more likely consciousness will occur. So you can see that we have here the level of consciousness. This is a tri-dimensional view. The level, the content, and the form of consciousness. Let me sketch the constellation between the three in different states. We already discussed that if you're in REMs, if you're awake, you have a high degree of form, you have a high level of consciousness, and you have a high degree of content. All three are high, as I assume when you listen to this talk. If you fell asleep and you start dreaming about the nightmares of neuroscientists and their research into consciousness, then you still have a high degree of content, but your level of consciousness is rather low. So you're basically here. High content, low level, and also your form is still somehow preserved because you still have content about the nightmares. Then finally you doze off and even you don't have nightmares anymore, your sleep is just deep. You come into non-REM sleep. You don't have contents anymore. Also your form decreases and of course your level decreases too. So you can see that your different states of consciousness can be quite well mapped on this tri-dimensional view. Okay, let me show you another example if you have a brain lesion. Let's say you have a brain lesion in your visual cortex. Here in the back, your occipital cortex. You cannot process visual contents anymore. So meaning your processing of particular contents is decreased. Whereas your form and your level of consciousness are more or less preserved. So all the other contents are not affected. You have a specific brain lesion and a lesion in specific content of consciousness. Now, how about the disorders of consciousness, like the vegetative state, coma, or minimally conscious? So, as indicated above, these patients are typically characterized by a loss and decreased level of consciousness. So you can see they're very low. And that in turn also seems to affect their form of consciousness, their resting state activity as shown, which is also shows decreased variability. And that in turn also affects their content of consciousness. So now you say, why do we need this third dimension of consciousness, the form of consciousness? We can explain everything by level and content. Next, disorders. So these are psychiatric disorders in schizophrenia. These patients have a normal level of consciousness, sometimes even too high. And they process all kinds of contents, but in a very bizarre way. They perceive the same content in a very different way. For instance, schizophrenia. They hear internal voices, auditory hallucinations. Sometimes they have the feeling that they are a different person, ego disorders. And their thoughts are chaotic and confused from the outside perspective. Thought disorder, as it is called. How is that possible? That's exactly, I would argue that these disorders are disorders of the form of consciousness. There's something wrong in the spatial and temporal structure of their intrinsic activity. While their level of consciousness is more or less preserved, as well as the contents of consciousness are somehow preserved. But the contents are integrated in an abnormal spatial and temporal way due to the changes in the resting state activity. If that is so, you would expect in these patients strong changes in the spatial and temporal structure of the resting state activity. The findings in the last 2-3 years indeed strongly support such a view. And that really maybe lends support to the form of consciousness. So again, you can see, back to our brittle objects, that the intrinsic features might consist in the spatial and temporal structure of the intrinsic activity, which is a predisposition. If that by itself is disturbed, you might have problems. You have abnormal organization and structuring of your contents in consciousness. So, if you want to summarize the whole thing, and this is, you have your intrinsic activity, which is here. It provides a certain spatial temporal structure, a form of consciousness. Spatial temporal organization is the putting together of the contents. And you might want to say that this is a neural predisposition of consciousness. In the same way that the floor here on which I stand, or the floor on which your chair stands where you sit and watch this video, is a predisposition for having furniture in this room at all. Without the floor, you would not have furniture. If the floor is tilted in a vertical way rather than being completely horizontal, any kind of content, any kind of furnishing of the room will be affected. And this seems to be the case in psychiatric disorders where the floor itself is abnormally tilted, meaning that the brain's intrinsic activity and its spatial temporal structures are somehow abnormally organized. Then you have the level of consciousness, as for instance in the vegetative state patients, or the so-called disorders of consciousness, like in non-REM sleep or vegetative state, or also in anesthesia. So there you have again certain changes in your resting state, but somehow the spatial temporal structure is preserved, but apparently some of the fluctuations and the variability and the metabolism are no longer sufficient. That affects your level of consciousness. And that may be what is recently called a neural prerequisite of consciousness. Without this, you cannot have consciousness. So this is basically like the legs of your table. Without the legs of the table, you cannot have any table. Even if you just have the plate without legs, you will not have a proper table, unless you sit on the floor. Or like without the legs of the chair, you cannot have a proper chair. So this is basically a neural prerequisite. And then you have what you call the neural correlates of consciousness, which are associated with the contents of consciousness and usually associated with stimulus-induced activity. And those are, for instance, deficient in selective brain lesions, particular regions. So the assumption is now that you have a continuum from the pure non-conscious to the neural predisposition, neural prerequisites, neural correlates, and then to what the philosophers call phenomenal consciousness. You have a subjective experience of consciousness. Such phenomenal consciousness is to be distinguished from other forms of consciousness like access consciousness or reflective consciousness, which basically means that you become aware and reflect upon the contents of your consciousness. This is about how the subjective experiential component of consciousness comes about. So, and now a couple of slides towards the end, I told you about what brain imaging can tell us about consciousness. But maybe there are also certain limitations, or these limitations may be either principal limitations, so that they cannot be overcome, or they may be rather contingent limitations, which can be overcome by applying proper means. So in one of the things which is, for instance, the kind of conceptual framework we often apply in our studies on consciousness. So usually we consider, and this is a tradition transferred from philosophy, that consciousness is a higher order function. So this is illustrated in this slide. Usually it is considered you have sensory-motor function is the most basic function, affective functions, cognitive functions, social functions, and then the result of all this is what you call phenomenal consciousness. And then you have a certain reflection or access to the contents, which, for instance, Ned Block described as access consciousness. So here, consciousness, and phenomenal consciousness in particular, is a higher order function of the brain. It's at the highest level, it's the highest level of integration. This is the typical view of philosophy, which has been more or less transferred also to neuroscience. So there has been a lot of search for consciousness and its mechanism in consciousness, more recently somehow in sensory-motor functions and also in affective functions. However, the data I presented you and the central role of the intrinsic activity seem to speak a different language. Here, phenomenal consciousness seems to be a most basic function. I should have written here the intrinsic activity. And based on that, you have the different kinds of functions, sensory-motor, affective, cognitive functions. And then those may allow you to access the contents in your consciousness, access consciousness. But the phenomenal, the subjective experiential features of consciousness may be closely related to your intrinsic activity and its spatial-temporal structure. For instance, even during the night, when you dream, or now when you sit in front of this talk and dream about nightmares, about philosophers talking about consciousness, then you have consciousness in your dreams, in your sleep, despite the absence of any specific sensory-motor, affective, or cognitive functions. So that suggests that your ongoing resting state activity must have certain features which somehow make possible phenomenal consciousness. So, and that conceptually, it really turns things around. You no longer consider phenomenal consciousness as a higher order function, but rather as a basic function of the resting state in its intrinsic activity. And as I said, the spatial-temporal structure of the intrinsic activity may be central for that. So, the question is, how does all relate to philosophical problems? You know that the philosophers like to speak of what they call hard problem and easy problem. Roughly formulated, the easy problem describes the relationship between consciousness and cognitive functions. For instance, the relationship between attention and consciousness. Long time, consciousness has been associated with attention, but the data more recently show that it is rather likely that consciousness is different from attention as well as from other cognitive functions. That's the easy problem. How about the hard problem? The hard problem states, why and how is there consciousness rather than non-consciousness? So what we need to show is how is it possible that the pure non-conscious of the brain is a gray, pulpy mass, you remember my initial statement, is transformed into consciousness. That is the question. How and why is consciousness possible rather than non-possible? That's what philosophers call the hard problem. And I would suggest that this distinction between neural predisposition, enabling condition, neural correlate, describes different steps how the purely non-conscious gray matter of the brain is transformed into the consciousness of our experience. And I bet that, I hope, in 10, 20 years, there will be many more steps sandwiched in between. This is probably a very early, rough categorization, and we need different steps. But I would argue that probably the intrinsic activity based here on this level may be central in mediating and making possible the distinction from non-conscious into the kind of processes that in turn make possible consciousness. But as I said, we don't really know much about at this point. So, And that ultimately leads us to the end of my talk. Why is it possible that the intrinsic activity is so central for consciousness? We currently do not really know, but at least it might be a suitable candidate, and we can develop hypotheses about its potential role in consciousness. And this is exactly what I try to do in these 2 volumes, in Unlocking the Brain, Volume 1 Coding, Volume 2 Consciousness, where I assume that the intrinsic activity and its particular way of encoding neuronal activity might provide a key to unlock the brain and how it generates consciousness. Thank you very much.